Howdy. Pretty good. How are you? Oh, yeah?
Okay, we go to the second or the state game and the game before that.
Yeah. At least you don't have to yell too much during the game, right?
During the game?
Yeah.
Oh, yeah,
Oh, well, never mind. Never.
you had to get in the other team's head.
Sure. Oh, yeah. I remember my wife when she was playing softball, their team would have all these different chants and kind of stuff that they would do all the time. Okay. So code today is RIX UXP. Bell work is a really weird ACT question, number 53. So supposedly these are equally spaced dots are marked on the side of a regular polygon with a dot at each vertex. The distance between consecutive dots is the same for all sides. The figure of this one shows 4 equally spaced dots for a triangle. Which of these expressions would represent the number of dots for any regular polygon with n equally spaced dots, including one at each vertex, marked on each of its s sides? Look at that. I'll give you 3 minutes to try that one, and then we'll go over it, and then we'll do footprints in part 1. Okay, so let's go over this. So what do you think we should do to find the number of dots? Well, first instinct, you would think you have n dots on each side times the number of sides, right? So that would give you n times x. But that doesn't quite work, right? Because the problem is that there's one at each vertex, right? That's being double counted then. So for our example, if we did that, this has 4 dots on each side and it has 3 sides, right? So this would be 4 times 3, which is 12. But in reality, if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, this really only has 9. So what could we do to 12, right, to make our answer what it's supposed to be is 9? Would -1 do it? No. Would -s do it? Yeah. 12 minus 3 would give us 9. So this is a contender. Would +s do it? No. Would -n do it? No. 12 minus 4 would be 8. So really, if you just use the example and just test the example's formulas against how many dots it has, you'll get the answer. You could also think the idea here is I'm doing n times s to get the total number of dots, but since 1 is included each vertex, that means for each side, I have 1 that's being double counted. So if I subtract 1 for each side minus s, then you'll get the true number of dots. Isn't that cool? Yeah, that's a cool one. So this is a problem where I just encourage you, whenever you get to these high number of problems that seem really complicated, make it a simpler problem. That's my favorite ACT technique. Solve a simpler problem and then use the fact that this is multiple choice to get the right answer. Okay, today we're going to do inverse trig functions. We'll do it for sine, cosine, tangent, and then we won't get to C actually today. We'll only do A and B. So we're going to do sine, inverse, and then the inverse for cosine and tangent. The homework for today is due Wednesday, but it's I think half as long as a normal homework. It's only like 6 to 8 questions. That might be a little over half. But broke the lesson up into 2 parts because it's kind of complicated. All right, let's start with the first thing, inverse sine functions. So if you remember, this is review, so you don't have to write this down if you don't want to, but this is already in your notes. For any function to have an inverse, it must be 1 to 1. So for every x value, there's 1 and only 1 y value that goes with it. Or in other words, it must pass the horizontal line test. So for a function to have an inverse, it must pass the horizontal line test. None of the trig functions actually pass the horizontal line test, right? If we look at the graph of sine of x, it fails the horizontal line test because this horizontal line intersects it at more than 1 point. So that's a problem because we actually would want to be able to use inverse trig functions. So here is the solution that we will use so that we can perform inverse trig functions. For sine, what we will do is we're going to limit the domain to only be between -π/2 and π/2. Because in this interval right here, it does pass the horizontal line test, right? Every horizontal line intersects this graph only once. So if we restrict the domain of sine of x to only the angles between -π/2 and π/2, including the endpoints, then those are the angles that are in quadrant 1 and 4. And then you'll have no duplicate y values. So it will pass the horizontal line test, and we will denote this inverse function in one of two ways that are used interchangeably. Arc sine of x is the most common, or sine with this superscript of -1. Note that this is not sine raised to the -1 power, even though that's exactly what it looks like. This is inverse sine. You might ask, well, Mr. Lake, what does it look like when it is sine to the -1 power? And that looks like that. I know that those look like exactly the same thing, which is why this notation is garbage. However, it is still a commonly used notation. If you look at your calculator, right, the sine, cosine, tangent buttons in blue above them, your inverse trig functions, all use this notation. I prefer the arc sine notation, so I'll use that more often. Hey. All right. So the other thing you have to remember for inverse functions is whenever you do the inverse of a function, if it passes the horizontal line test, it exists. And what it does is it switches your inputs and outputs. So the arc sine function will take an angle and give you a y value. So its domain are all the possible y values from -1 to 1, and its range, its output, will be the angles between -pi/2 to pi/2. So I'd make sure you write down this last line is key. This one, you don't necessarily have to have down. This one, I would make sure you write down. Arc sine has a domain between -1 to 1 and a range from -pi/2 to pi/2. All right, does anyone need more time to write? Okay, let's see it in action then. So here's some more properties. So if you graph arc sine, there are two ways you could do it. One is, remember that you can graph any inverse function by taking your function and reflecting it over the line y equals x. So if you think, this is what the sine function looked like. Not quite. This isn't quite right. I'm not even gonna. It's gonna. Okay, I'm gonna try. It looks like that. That's really poorly drawn because it's not to scale. But if you flip this sine function, which looks like that, over the line y equals x, you get this arc sine function. An easier way to do it is really just to use your definition of what arc sine is, which again, I would make sure you write down these three formulas are really important. So the idea here is if the sine of an angle gives you the y value on the unit circle, then the arc sine does the reverse of that. It takes a y value on the unit circle and it tells you the angle that makes it. Again, only for angles in quadrant 1 and 4. So that using this definition is the easiest way to graph arc sine, because all you do then is you take all the different y values on the unit circle and you find what angles go with them, and then you plot those as points. Again, the y values being your domain and the angles being your range. Similarly, if your points are not on the unit circle, so if the sine of your angle gives you a ratio of y over r, then what the arc sine does is it takes that ratio of y over r and it will give you an angle. Again, only angles in the first and fourth quadrant. between negative pi over 2 to pi over 2. And similarly then for any right triangle, if the sine of an angle in a right triangle is opposite over hypotenuse, then what your arcsine function does is the opposite of that. It'll take the ratio and it'll tell you what angle produces that ratio. And really, these should only be answers in quadrant 1, since your ratio should never be a negative number in a right triangle. So again, what this slide is telling you is the sine of an angle gives you a y value or a ratio. The arcsine does the reverse of that. It takes your y value or your ratio and it tells you what angle produces it. So to solve these problems is actually very similar to what we were doing before. We're just like going backwards through our steps. Would you like to see an example, or does anyone need more time to write? No? Okay, so let me show you an example. So for example, these are the first type of problems I think you'll see on the homework, is they'll ask you to find the arcsine of different ratios. So if I want to find the arcsine of negative 1 over 2, again, it's the reverse of the steps that we did before. I will find the y value first. So if we look on our unit circle, where is our y values at negative 1/2? Because here has a y value of negative 1/2 and here. So that's going to give me the answers 7 pi over 6 or 11 pi over 6. Those are the angles that produce a y value of negative 1/2. However, if you remember, a function can have exactly one answer, right? So both of these cannot actually really be the answer. So that leads us to step 2. We then need to use our range. So again, the only answers we should get are between negative pi over 2 and pi over 2. And again, those are the angles in quadrant 1 and 4. So 7 pi over 6 cannot be the answer because it's not in quadrant 1 or 4. It is not in our range. 11 pi over 6 is in quadrant 4, but it's not in the range. However, that's an easy thing to fix. I'm just going to find what angle is coterminal with it. So I'm going to take 11 pi over 6 and subtract 2 pi to get negative 1 pi over 6, which is in the range. That is between negative pi over 2 and pi over 2. So the arcsine of negative 1/2 is negative pi over 6. And again, you get that in 2 steps. First, you find the y value that it's giving you in your unit circle. And then you identify which, you'll almost always get 2 answers. There's only 2 y values that'll give you 1 answer. So you almost always get 2 answers. And then you have to say, right, which of those answers is in the right quadrant? And if your answer is in quadrant 4, you will almost always, you'll have to do this extra step where you subtract 2 pi to get the coterminal angle. But really, I mean, if this is pi over 6, then we know this is negative pi over 6, right? All right, let's try another. What about this one? Sine inverse of square root of 3 over 2. First step, I'm going to find my y value. So where is square root of 3 over 2 as a y value in the unit circle? Again, it's in 2 spots, here and here. So my possible answers are 2 pi over 3 or pi over 3. But again, a function can only really have one answer. So which of these answers is in the range? Well, it can't be this one because that's not in the right quadrant. And if your answer is in quadrant 1, you don't actually have to do anything more to it. Pi over 3 is between negative pi over 2 and pi over 2. So the sine inverse of square root of 3 over 2 is pi over 3. All right, does that make sense? Sweet. It's your turn then. All right, I'm going to give you 3 problems. Find each of these. Again, 2 steps. Find the y value on the unit circle, and then tell me which angle is in the correct range. Or make sure your answers are in the correct range. All right. So where is a y value of 1 on the unit circle? What angle? There's only one. Yep. Pi over 2. It's the only time we get a y value of 1. So this one is the only time, well, actually this and one other, when negative 1. When you'll just have one angle and then that's it. That's your answer. What about square root of 2 over 2? Well, that happens in two spots. Here and here. Which of those is the correct answer, though? Pi over 4 or 3 pi over 4? Pi over 4, because it's in quadrant 1. That's the only angle that's between negative pi over 2 and pi over 2. All right, last one. What about 2? Where on the unit circle is our y value 2? Well, never. The highest y value is 1, right? So the answer to number, or to C, is undefined. That is not in the domain. Remember, the domain is between -1 to 1. Yay? Okay. Well, really, if that makes sense, all of this makes sense to you so far, this is it. This is class. Because for cosine and tangent, it's the same thing, just with the different quadrants that you look at. So for cosine, in order to make it pass the horizontal line test, we can't use the same interval, right? If we did negative pi over 2 to pi over 2, it would still fail. So to make it work, we go from 0 to pi. So it uses angles from quadrants 1 and 2 to get its answers. For tangent, we use the same interval as we use for sine, between negative pi over 2 and pi over 2. The only twist with this one then is that there is no limit on its domain. Because if you look between negative pi over 2 and pi over 2, it goes forever downward and forever upward. So its range is negative infinity to infinity. And again, if you switch the range and domain to make your inverse, that means the domain is negative infinity to infinity. But its range is exactly the same as sine, with one change. We use parentheses now instead of brackets between negative pi over 2 and pi over 2 because the endpoints cannot be included as they are vertical asymptotes. Tangent is undefined at those endpoints. So same range, just you can't include the endpoints. While you're writing this down, I should say that as you do these problems, it's easy to mix up what quadrants go with which functions, or it can be, since cosine's weird. So you can check your answer with your calculator, sort of. When you do the arc sine inverse of an angle in your calculator, it's not going to tell you that the answer is pi over 6. It'll give you the decimal for pi over 6 instead. But you can still use that to check your answer. Just turn your answer to a decimal, right? And see if it's the same decimal. So for a lot of these problems, you can't really use the calculator to find the answer, but you can use the calculator to check it. I mean, eventually, once you have all the decimals of all the different fractions of pi memorized, I suppose. That's a lot. That's a lot to ask. And again, when you graph these, which I don't think it asks you to do a lot of, you can graph these using Desmos. Or by taking your function here and flipping it over the line y equals x. Get that, flip it over it. But the easiest way is just to pull up the unit circle and plot some points. All right, so you ready to see some examples? All right. So for example, if we want to find the arc cosine of the square root of 2 over 2. Again, we'll pull up. Why did I copy the unit circle? Mr. Lake, come on. Okay, if we pull up the unit circle, cosine takes an x value and gives you an answer, right? Or sorry, cosine takes an angle and gives you the x value. So we need to look where on the unit circle do we have an x value of square root of 2 over 2. And that happens at two spots, here and here. Ooh. But again, so my two answers are pi over 4 and 7 pi over 4. I should say my two potential answers are pi over 4 or 7 pi over 4. But which of those is in the range of 0 to pi? Oh, not this one. That's too big. That is bigger than pi. So it's not this one, it's this one, which again should make sense because these are the angles in quadrants 1 and 2. And you can see from our unit circle that this is the answer that's in quadrant 1. This answer is in quadrant 4, which again is not in the range. The nice thing about arc cosine is since the answers are always in quadrant 1 or 2, you'll never have to worry about coterminal angles. You can just pull the answer straight from the graph. Tangent's tougher. So if you remember, the tangent of an angle gives you y over x. So the tangent inverse would take y over x and give you the angle. So what this is telling me, to find the tangent inverse of 0, I have to find out when does y over x equal 0. Well, what's the only way that that could happen? If y is 0. So that means y is 0. So now I'm looking on the unit circle. Where is y 0? And again, y is 0 at two spots, here and here. But remember, tangent only takes the answers that are in quadrant 1 and 4. So 0 has to be the correct answer, and pi is not in the range. So again, my potential answers are 0 or pi, but the only one that is in the range of negative pi over 2 to pi over 2, which again is your angles in quadrant 1 and 4, is 0. Pi is not between negative pi over 2 and pi over 2. So the tangent inverse of 0 is 0. All right, and again, does everyone need to write this? Okay, so if I stop share, reshare, whole screen. So again, after you're done with these, you might say, oh, I'm not sure I did that right. There's a lot of steps. If I do the cosine inverse of the square root of 2 over 2, it'll tell me, oh, I have mine in degree mode. Radians. All right, try that again. It'll tell me the answer is 0.7853918634. If I take the answer we got, pi over 4, you see that those are the same decimal. For tangent, if I do the tangent inverse of 0, I get 0, which is the same answer we got. All right, your turn. Why verify? Why is that? Look at this. Verify your answers with a calculator. This is the cosine inverse of -1. That's what that says. Cosine inverse of -1. Okay, so tell me what's the cosine inverse of -1, the arctan of -1, and the arc cosine of 2. I'll give you 3 minutes to try it on your own, and then that'll end class. Remember, cosine takes an angle, it gives you an x value on the unit circle. So the cosine inverse would take the x value and give you an angle. So you need to look where on the unit circle do we have an x value of -1. Tangent takes an angle and gives you y over x. So you need to say the arctan then would take y over x and give you an angle. So I say where on the unit circle is y divided by x -1? Which I think you have a table in your early chapter 4 notes that you could use for all the different tangent values that might be useful. There might also be a table in this section of the book that you can look at. All right. So if you look, where on the unit circle do we have an x value of -1? That only occurs at one spot, right here at pi. So the arc cosine of -1 is pi. All right. Where do we have a y divided by x value that equals -1? Well, there's only one way that could be true. And that's y and x are the same number, right? That's the only way it could divide to be 1. Now, the only way it's going to be negative is if they have opposite signs. So that only happens in 2 places where they have the same value but opposite signs. Here and here. However, this answer is not in the range. The range are the values in quadrant 1 and 4. So this is not in the range. This is the answer. And I believe that's, what is it, 7 pi over 4 right here. Now, 7 pi over 4 is not in the range either, but it is in the right quadrant. So if you subtract 2 pi from it, you get negative pi over 4, which is in the range of negative pi over 2 to pi over 2. And again, for this one, we're looking for an x value of 2. That never happens. The largest x value is 1. There's nothing to the right of 1 on the unit circle. So this is undefined. Questions about that? Okay. There's one more thing on the homework that reviews transformations. If you need help with that, it's in the lecture notes that you can check out. But otherwise, have a good day, everybody. See you Wednesday. Bye.